everyone, how are we doing? I hit the intro button today. We got some questions from Tiffany and Leah and Tara and Kayla. Good to see everyone here. We got some bunch of Chapter 8. Love it. Let's start out. Tiffany's got the first question of the day with Chapter 12. Let's hop over here to My Pearson. And let's get My Pearson going. How is everyone doing today? Mewbot is finally awake in the chat. We had to reset Mewbot. If you're here, it was Tuesday. Mewbot went away. Mewbot, he gone. He went away for a bit. He's back now, though. Mewbot is back, doing just fine. I'm good, Tiffany, myself. Doing great. I didn't yet. Last class, I didn't even have it on live chat the whole class. When you load up YouTube, it goes to top chat instead of live chat. And so, we'll go into Chapter 12. We're going to do some probabilities. We'll go into more detail on this next week. This is a really good question, Tiffany. We actually base a test question on this or two. Tiffany's asking about, this is the late to class one. Yeah, so let's look at this one. Late to class. And so let me see right here. We're going to do the late to class one. This is Chapter 12 probability we're about to do. Here we go. Wait, that's cars. We almost got it. More car stuff. Here we go. Let's check this out. This is actually really good. Leah, good to see you here. Feel free to ask any questions. We got another question from Tara. Put the questions. Leah and Tara have a question about Chapter 8. Throw the Chapter 8 questions on here, and we'll do some Chapter 8 right after to say, hey, this problem right here on like wildfires or CO2, whatever you want, we will do it. And let's hop in here and start looking at some Chapter 12. Let's go take a look at this on Stat 1. Ears acting up a bit weird today. Yes, the fastest cyclist. We will do that next year. So this question is about probability. This is Chapter 12 on probability. And what are we looking at? A student figures they have a 26% chance of being let out of class late. So that's the probability they're out of class late. If he leaves class late, then he has a 23% chance of missing his train. What's really cool about this one is there's a lot of parts to it. So there's a lot of parts to this question right here. We'll take a screenshot of it. And then we'll hop over here and we'll show what's going on. So we can kind of turn this into a more advanced problem with asking what could occur. So think about this. Two great questions right there. With there's two things and they could occur 4 total ways. Tell me one thing that could happen right here. Like he could get out of here. I'll tell you one of them. He could get out of class late and miss the train. So actually, there's only 3 things. So there's 3 things that could happen. I stand corrected. It's a little bit complicated of a question when you think about it. So he could get out of class late and miss the train. That's one of the things that could happen. So let me write that down. We'll write down get out of class late, ... misses train. So that is something that could happen. What is another thing here that could happen? So he could get out of class late. And the probability of getting out of class late is this. We'll solve this here in a moment. He could get out of class late, and then he could miss the train. So what's another thing? Can I email a TA for feedback from my first try? Email me, and I'll send you some critique of it, Jake. Email me. bstevens@utk.edu. Email me. He could get out of class late and miss the train. Keyword right there, and. So he could get out of class late and miss the train. What else could happen right here? That's the event at list right there. So he could get out of the class late and miss the train. Anything else could happen? So think you're in class and you're like, oh man, I might get out of class late. Oh, if I get out of class late, I might miss the train. But what's another thing that could happen? So out of all the things that could happen, what else could happen? Or you can get out of class late and miss the train. That's one thing. So what else could happen? We're just talking about, you're just saying, oh man, I might get out of class late and miss the train. There's your backpack right here. You're holding on to your backpack. So what else could possibly happen? My hair's been so weird lately. Is there anything else that could happen? Can you only get out of class and miss the train? Is that the only thing that could possibly happen out of everything that could occur? Get out of class, miss the train, get out of class late, and make the train. And so here's the confusing part. So with this, you could get out of class late and make the train, but apparently if you get out on time, you will always make the train. What is the probability of getting out of class on time? what is the probability of getting out of class on time? Now, this is a complicated, or it's not that complicated, but this is the complement of getting out of class late. Because either you get out of class late or you get out of class on time. So what is the probability of, here's being weird. What is the probability of getting out of class late, or on time, excuse me? What is the probability of getting out of class late, on time? 74%, it's just the complement. We call this the complement. Sorry, everybody. Ears being weird, don't like it. So now we have two other events right here. 74% is the probability of getting out of class on time. The probability of getting out of class late and then making the train, we'll do the easy one. Probability of getting out of class late is 26%, and then you miss the train is this right here. So this is the probability of getting out of class late and then missing the train, and that's 0.0598. 0.0598. Now watch this. We're missing a 0 right there. Magically, I'm going to find the last probability, and I'll show you why. There's that, and there's the last probability, 20.00. And we'll just put in equals right here and do 20.002. And this is what mathematically is equal to getting out of class late and making the train. How did I know this? Think for a moment, because this is some tricky stuff. I'm showing a little bit of advanced works right here. How did I possibly figure this out? How did I get that right? So I'll show you how I got it, and then I want you to think, well, how did Brian know that? How did I know that? What do you think if we've listed out everything right here, so that's get out of class late and misses the train, get out of class late and makes the train, because making the train has a 77% probability. So that's this one right here. My color change pens are still doing their things, and this one right here. Where did we get the 0.77? That is the probability that he makes the train. So if he gets out of class late, the probability he makes the train would be this. Does that make sense how we found the probability of making the train? Because he either will make the train or not make the train. So he either makes the train or does not make the train. The probability of not making the train is 0.23. The probability of making the train is 0.77. The probability of getting out of class late is 0.26. The probability of not getting out of class late is 0.74. These are what we call complements of each other. So if we have the probability of A, then the complement, it's right here, complement of the probability of A is equal to 1 minus the probability of A. So yeah, it's making sense, right? So the complement is 1 minus, which is actually the trick I did for the last one. If you're like wondering, well, still, how did Brian get that probability without solving this mathematics right here of the probability of getting out of class late and making the train, which we've written out here mathematically? Think about this. What must the set of everything add up to? What would all of these probabilities add up to? If I add up all these probabilities and it's everything that could occur, hint everything, then what would it add up to? If we were to add up those numbers, 0.74, 0.2002, and 0.0598, Andrew right there, excellent work, it would add up to 1. So if I'm missing one of these probabilities, like let's say I didn't know this one right here, what could I do to find the remaining one? And it's down here in the rule, because now if we know some probabilities, we could find the other one, which is the complement, which is the portion we don't have, the remaining set of possibilities. And so what could we do right here to find this probability? Can you think of the mathematics? Now, I could solve this right here, but I solved it a little different way. And this is good practice for this chapter if you know how to solve these things this way, understanding what complements are and how if you're missing an event, it's like, well, everything adds up to 1. So what could I do to find out the remaining probability without solving this mathematics right here, which could come into use for some problems? To solve this without solving the equation, I already know 2 probabilities and I'm missing a third. You could write the full equation that 1 equals question mark, plus, and then we could do 0.2002 plus 0, this right here. Like those probabilities must add up to this. And we could subtract, and that's what we're going to do algebraically. So if you're wondering what we're doing, it's the algebra right here that we're just taking these and bringing them over to the other side, and we're just subtracting them from this. So this is what we're algebra doing. We're saying, okay, and it's the same idea of the complement. Like we're trying to find the other portion of it. Like, well, we don't want these. We want the other side of it. So once again, we could do this, and this is like a reverse of what I was doing. Take 1 minus and do this right here, and then subtract from it the remaining. And now we get 0.0598, which you don't have to do because you can just solve by doing the actual mathematics. And so does that make sense right there, Tiffany and Kayla? So this one right here, if we're finding out the probability he gets out of class late and misses the train. So the only way he misses the train is if he gets out of class late. If he gets out on time, he'll always make the train. So we don't even have to worry about that kind of sub-conditional probability within it. So this should be the answer right here. Great job, Tiffany. We're going to do some chapter 8 coming up here. Probability 1, 2, 3. Oh, really? It's going to round? You're going to be good? Nice. Got a little worried with that round right there. That's got it. We're going to head back and do some chapter 8. Let's do it right here. Put those questions in the chat. We got 2 more questions right now, but the questions go quick. So put questions in the chat. Say, hey, can you do this question? We'll talk through it. We love talking the theory too to understand kind of more in depth on the problem. That's the biggest thing. Don't look at these just as problems where you just have to get a right answer. You want to conquer the theory behind it, and then the problems get a lot easier, especially when you get to the test. If you understand the theory. My ears are being so weird. I don't like it. Over 100 years, the fastest cyclist time. Love it. Here we go. Stat 201, Chapter 8, as Brian's ear makes weird noises. Stat 201, Chapter 8, fastest cyclist times. Let's do this. So we have, oh, you bet, Leah, we got this right here. You bet. And so fastest cyclist times are on the screen right now, and we need to see what's going on right here. Ooh, this one is not going to catch me today like it caught me last time. So we have right here a plot, and it's important to look at the data. Now, we're going to throw this in jump here for a second, but one thing to know about this data is that there's gaps. Because of the world wars, you're seeing a gap right here, and I think there's another gap in the data. What do I mean gaps? Do you see the gap? There is no data starting where? Tell me. We're missing this year to 1918. I know, right? I'll show you the good way to find them. What is the first year we're missing right here? Do you see it? The first year we are missing, if you look at this as a series, a time series, which is a time-ordered plot. The first year we're missing, which we do not have data on, which would be what year? And it goes to 1918. We don't have years from this year to 1918. Important to just see that. Be like, oh, we don't have data for those years. Starting at this year to 1918, we don't have data. So on 1915, great job right there. Oh, and then we'll do we got another chapter 8 and 12 after this. So, and then we're also missing from 1940 to, and then, so we wouldn't do these equations, or you might have to look at stuff. You might have to look at data. We don't really write test questions like this. What we usually do, and we're going to now, since we know what it should look like, we're going to copy it to the clipboard. Yeah, we'll be doing that. We got your second line. You got it, Tiffany, you bet. Do I not have jump open? Oh yeah, we crashed jump during class. Haha. We crashed it during 474 today. Reloading jump. I'm trying to download the new jump. Won't let me download it. Okay, jumps license. It keeps asking me for my jump license every time I restart jump, and I just don't know why. It works. Still got jump. So we're going to go to edit, paste with column names. Remember, paste with column names because there are column names. If you do not paste with column names, it'll look like this because it puts the column name in the first column and you will have a bad time. You don't want to do that. Not good. Not good. So now that we have quantitative variables, blue means quantitative, we can go here to analyze fit y by x. Analyze fit y by x is a bivariate analysis, which will give us a scatter plot. When we say, why do people have a fastest cycling time? Maybe it's the year that explains it. So now you can see our plot right here, and you can see the gaps in the data here. I'll make it even bigger so you can see. But there's gaps in the data here, big gap in the data there, and then there's a gap in the data right here. So we have 2 gaps in the data. Now we go here and we go to fit line, and this fits the regression line. With it fitting the regression line, we can get things like the R-squared. So this is where it becomes a little bit test relevant. To copy the data again, make sure you have your data open right here and go to the copy button. Here you are, and then go to the data table right here. And now go to copy to clipboard. Once you copy to clipboard, hit Control-C or Command-C, which will copy it. and don't change the tab delimiter or anything. It'll be good. And paste it. And then when you paste the data, go to a new data sheet inside of Jump. So hit Control-N or Command-N. File, new data table. Oh, are you on this step right here with me, Leah? Have you copied it? I'll pause right here. Are you on this right here with a new data table? Do you have a new data table open, yes or no? I'll pause right here. So you should have it copied right now. So as long as you have it copied, and then go to File, New Data Table. We want to open up a new data table. So you should see a new data table. Yes, I've copied. Okay. Do you have the new data table open? So we should have a new date. No, you're fine. Don't worry about it. Don't worry about it. Do you have the new? So you should go to File, New Data Table. And so tell me when you have the new data table open. You got the new data table. Okay, don't click inside of it. Don't click inside of it. Tell me yes or no. When you go to Edit, Paste with Column Names, are they blue? So Edit, Paste with Column Names, and they should appear in blue. So go to Edit, Paste with Column Names, and they should appear in blue. Tell me if that works. You're like, yes, it worked. So, and feel free, just feel like you're going too fast. I never want to, because if I'm going too fast and it's not helping anybody, that's not good. So thank you, Leah. 100 points, Leah, right there. Thank you for slowing me down. I appreciate that. And so how are we looking on this? How are we looking on this right here? This is looking pretty. So when you do this, edit, paste with column names, it should be blue. That's key. Is it blue? As long as it's blue and looks like this, you're good. And now we've got the data pasted into Jump. Awesome, awesome, awesome. Thank you, Leah, very much. I'm throwing another 50 points right there. Thank you, Leah. And now we go to Analyze, Fit Y by X. You got the blue, nice. Make sure to paste with column names as you did. If you don't paste with column names, it'll go red and then just restart. Ways to fix it, but it takes a lot longer. Analyze, Fit Y by X right here is going to allow us to do the bivariate visualization because a Y and an X. So you can just take the variable year, which is going to be the explanatory variable. Year is going to explain why we have a certain average speed. So we're trying to explain the speed of the cyclist based on the year. So this is going to be year as the X, and the response is why do they go a certain speed? So it's analyze fit Y by X, and then we put the Y variable up here, and we put the X variable down below. We click OK. I'm just kind of extending the plot to make it bigger. And then we can go here to the red arrow and fit line, and that'll fit the regression line for us. So this will add a regression line, which this question doesn't have us do a regression line, I don't think, but for other questions, it might. Just knowing how to read regression output is going to be important for the next test. So we click OK. Boop. How you doing, Leah? Is everything looking good? Yes or no? Y or N? How we doing? Pretty good. And now we can see 87.9831% of the variation. This is the R squared. Percent of average speed of cyclists is explained by the year. Have cyclists really gotten this much faster? When's the data go up to? Goes up to 2011. They need to update the book. Man, have they really gotten that much faster? What happened to them during this period? Like twice as fast. Technology or something? Why did it dip? So with this, what we're looking at right here is a mostly linear pattern. And they're going to try to trick you at the end of this. We see here the intercept. We might need these for one of these. Here's the intercept and here's the slope. Important to know that the intercept and the slope are also down here, and the p-value is the significance of the model. So this p-value right here tells us that the slope is statistically significant. Awesome. The intercept is negative. You might say, well, that's not a negative intercept. Do remember that the intercept would be at 0. So it's a little bit crazy right here, but the intercept is all the way back here. The intercept, and it might be easier if I just do this. It was like, what, negative, something like that. There, yeah, it's ridiculous. So the intercept's way back there. This is not a good view of the model right here. McDonald's was founded. Wait, what? I'm so confused. Explain in greater detail, Kayla. Founded? Like when McDonald's was founded, 1918 or something? So during the dip? Oh, cool. Yeah, I should watch that movie about it. I think, did my fiance watch it? And I didn't? Why would I not watch it? I've heard it's a good movie that it's got Batman in it. Michael Keaton, I think. So here we are. Here's the missing, the dip in the... Oh! They were all eating McDonald's at that point. You're here lurking. Awesome. Some 50 points. You can see right here we have the missingness in the data right here. We are missing data points here and here. This is the right graphic. There is a positive... We do need the equation. They describe the relationship. There is a positive with a general linear trend missing the data. I hate this question for a reason coming up at the end here. So now we need the B0. Now, please remember, this is where I've seen mistakes. I've looked over people's assignments. This is B0 making it the what. When we write regression equations, because I think a lot of people go back to algebra, B0 is the what. So don't do algebra here, because you put things in the wrong spots. B0 is when x is equal to 0, making B0 the what. Now, don't put B0 there, because that's just the notation for it. But when we do regression equations with statistics, we call it B0, and that is the value of the what. Important things to know. We're reviewing chapter 7 a little bit right now. And this is where Jump's going to rescue us. So B0 is the value of the what. Because remember, it's the y-intercept. Great job right there, Kayla. Excellent work. B0 is the intercept, and B1 is for each 1 unit change. Remember, B0 is when x is equal to 0, and B1 is for each 1 unit change, and hence why it's connected to the x variable. So now we need this information from our analysis. Be very careful because this is negative. Please note the intercept is negative. This is literally the average speed right here, the y value predicted. So that's the same here. And then this is the intercept. And then this other one is the slope. Look at how it's connected to year. Make sure to copy paste these in accurately. Mistakes do happen right here. Round to 2 decimals is needed. Round the year coefficient to 3 decimal places. So this will round to 2. Please tell me if you make like a tiny error. People have, and I usually give it back. And if you reverse them, though, that is an error that's really bad. If you reverse them, that is a very bad error. So do not reverse them. Yeah, I'll take a look at that here, Lillian. You bet. Sorry, my ear is acting up. And so with this right here, we have the intercept and the slope, and make sure to take that from jump output and know where those values are at. Also make sure to know that this would say at year 0, which is an extrapolation of the model, we'd expect the average cycling speed to be negative 266 miles per hour, which is not making sense. For each additional 1 year increase in years, we expect the average cycling speed to increase by 0.153 on average. That's the interpretation of the slope. Doesn't hurt to interpret those in practice. Are the conditions met? Now, this is where they got me last time, but not today, my Pearson. Not today. No, the relationship is not met. So the relationship, even though we say it's mostly linear, that's why I hate this question for some reasons, the relationship is not straight enough in the early part of the 20th century. However, everything else is met. There's no real outliers. The variables are quantitative. It's mostly linear, and they're talking about this dip right here, and they're going to say it's not straight enough. Hate this question for that reason. But they'll try to trick you right there at the end. I don't know. One of these days I need to talk to my Pearson rep and say, you do say up here that it's generally linear. So all of these say, this one says generally nonlinear. But they're talking, it's such the things that statisticians fight over. And this is what the great statistician war was over, is this question right here. Because it's mostly linear. Does it have a big problem here? Yes, no, maybe. But yes, so especially seeing this right here, make sure this last one is like this. Can definitely catch you off guard. I think we have another chapter 8 problem, then we're going to do a chapter 12, and then we'll do some BS 474. Great job, everyone. A little tricky at the end there. Good question and good stuff reading jump output. So if you're looking for a good review of jump output, that question is a great way to review jump output. And to make sure you can read it, you will see jump output on the test. So knowing how to read the jump output is very... Sorry, my ears are so crazy today. I hate it. Jump output, very important to know how to read. The other question from chapter 8 was... Chapter 8... 3 month... Tara, thank you so much, Tara. Tara, we're doing next question next. 3-month bonds from 1950 to 1980. 3-month bonds. The 3-month bonds. You're welcome, Tara. Here we go. 3-month bonds. Great job, Leah. Leah, and you also got another 100 points. Congratulations, Leah. Great job. I love it when people swing by, ask the questions, walk through it, understand how to solve them, and make sure they don't make those small little errors that sometimes make you get like a 96. If you get 96, great job. Don't worry about it. But we want you to get those 100s here. That's what we're here to do. Practice the material, learn the concepts. Here we are, Chapter 8, Bond Rates. Let's do this. So here we are with Chapter 8, looking at the bond rates from 1950 to 1980. Now, here's a confusing thing. This is years since 1950. Now, we were just looking at some jump output a second ago with the previous question, and you'll notice whenever we make a regression model, we have two things. Now, don't worry too much. I'm just showing you a regression model. Promise. What two quantities will we get when we make a regression model? What two quantities will we need to talk about when we make a regression model? And so it's a totally different model, but also illustrates that whenever we're making a regression model, we'll have two quantities. We'll have this quantity here, and we'll have this quantity here. So what are the two quantities we have that we always interpret? So what are they? They didn't call it this right here. They're calling it something different. If you notice, that's on the x-axis like mine is down here. So look at the similarities between these output. Intercept and slope. Tara, another 100 points right there. Right, the intercept and the slope. We have an intercept and a slope, and they're getting down into this right here in just a moment. The correlation is going to be R. Remember, correlation is R in notation. So good note to have if you don't have it, write down. Correlation in notation is R. So if we were to square R, we'd get this. So what do you want me to do to get, sorry about that. What do you want me to do to get correlation from R squared? And let's make sure we do the steps. To get correlation from R squared, take your R squared and do what to it? So be very careful. It needs to be like this. So there's my R squared. I know it's 80.2, which is 80.2% of the variation, explained in rate by year. But what should I do to it? There's the R squared as a decimal, because we write it as a decimal or percent. So what should I do to the R squared to get R? So I have R squared, but I want to get correlation now. I want to go backwards. So what should I do with R squared to get R? You're right, Tara. Great job right there. And then be careful. Now, this is correct. But what should I do after square rooting it, which we often catch people on the test? After square rooting it, I should do what? So now that I've square rooted, it's going to round to 0.90, I think. Yeah. After I square root it, always check the direction. Because when you square root it, it could be positive or negative. And so you have to look at this right here and say, is it going up or down? Is the slope positive or negative? And the answer is it is positive. So this is going to be 0.90 when rounded. That rounds pretty interestingly to exactly 0.90. Just check your rounding right here. Rounding to 2 decimals is going to round everything up starting right here to 0.90. So there's a very strong positive correlation right here. And just look at the graph and say, yes, strong positive. A little bit of an outliers there, but strong positive. On average, the interest rate increased during this period. Oh, increased. Just filled in that word automatically. At about this. So does this sound like the intercept or the slope? If I'm saying it's increasing by this rate, does this sound like the intercept value or the slope value? If I'm saying it increases by this rate, is this the intercept or the slope? It's going to be the slope. This is what it's increasing by. And don't times it by any sort of things. Round to 2 decimal places, good. And then starting from, so what it started at, that's what it started at right there. That's going to be the intercept. Jake, great job right there. Jake, good to see you. 100 points for Jake right there and everyone else. So wait a minute. 2 decimal places. No way. I've done this question many a times. Round to 2 decimal places as needed. Something seems weird. Oh, no, that's all right. That's all right. That's what it started at. My brain just broke for a moment. My Pearson won't let me delete an answer I have in the box. Let me know, Tara, if you get it wrong. If I want you to let you delete that answer and you get it wrong, you can tell me it's the only thing you get wrong. I will correct it. Just email me and say, hey, Brian, during office hours, I told you it wouldn't let me delete the answer. I'll even trust you. If you say I already calculated and it's this, I'll trust you. So don't fret over that. Thanks for being here and saying that. I've never seen that sort of error. I think this is correct. My brain broke. I thought that was the slope for a second. That's the intercept, which if you look at this, does that hit at about 0? That does hit at about 0. So that is hitting at about 0 right there. What does the model predict for 2020? Now, this is where we have to be a little bit careful. When we're predicting for 2020 and it says round to the nearest integer, we can use this equation right here. Let's put the equation on the screen at the same time. So this equation is going to be, that's so weird. Like my ear being weird. I hate it. So when we write our regression equation, we are trying to predict the rate. I knew it. That was crayon. And the rate, because that's the y variable, is equal to so that's the years. How many years it's been. This is the formula. The predicted y hat is equal to b0 plus b1x. And what value am I going to plug into years if I'm predicting for 2020? I think this is where the mistake, and I almost made this mistake last time, but what value will I plug into years if I'm predicting for 1920? What value will I plug into years if I'm predicting for 1920? With predicting for 2020, oh my gosh. For 2020, I'll plug, great job, Jake, right there, excellent work. I'll plug in 70 because that's how many years since 1950. So I'll plug in 70 because it's years since 1950. And if we're predicting for 2020, we'll plug in 70. So it should work pretty well because there's a lot of decimals being carried. We're basically just timesing this. The intercept is basically 0. It allows you to round it, and you'll notice right there we get 19.6. And yeah, the little extra change would help round it up. So if I'm rounding to the nearest integer, then what would this predict? And a good way to maybe look at this, I wish it would show it further out. But if we were to predict even further out, yeah, that'd go to about 20. Well, that's the answer. So, hey, good to see you, Kennedy. Feel free to ask any question you have on the stats stuff. So would we expect this to be accurate? I'm going to remove the wording right here. You'd say, Brian. That's all right, Kenny. You would say, Brian, you are definitely whatting with your model. By going to 70 years after 1950, Brian, you've definitely done a what of your model. This is a bad idea. It's going outside the X bounds of your model. Type the word in the chat for 100 points to remember it, to say, Brian, you've definitely blanked from your model. Gotten well outside the X-axis. I don't know if we should trust this. You're going too far predicting into the future. So I think you've done a what of your model. Your model is whatting away from the data. Extrapolation right there. HTT bringing in that 474 knowledge. HTT knows we're doing some extrapolation on our model right here, 40 years beyond it. Try to test yourself to make sure you know the answers to these without checking these, to be like, oh, well, that's an extrapolation of the model. And these can give hints, but when you test yourself to see if you know the knowledge and you get those hundreds, boom, when you got that 100 right there. You can do some really good practice to make sure you can know it. So if you got to the test, you'd be like, it's extrapolation because we're going 40 years beyond the X of the model. And that's what extrapolation is. Now, technically, you would extrapolate below the model, but it's anytime you're outside of this X boundary of the model. So you can think about another model right here. We'll just do some classic models. Do we got this stuff? Where's my survey 10 data? Survey 10? Survey 10? Survey 11? Yeah, survey 11. Here we go. Here's survey 11 data. And if you think about this data right here, we'll go to predict somebody's height from their weight. It's just a regression model right here predicting height from weight. And let's fit the model. And when would this model extrapolate? Last question right here on regression. Then we're going to do a little more probability than some 474. When does this model extrapolate? When does this model extrapolate? When would Brian's model be extrapolating? And I'm going to help by putting in some stuff right here. When does Brian's model extrapolate? There was a size for these. Guess not. I always thought you could change the size of points and jump. When does this model extrapolate? Because there's a thing usually people forget about extrapolation, and I'm trying to point it out with this example. When does this model extrapolate? swear there's a way to change point size. Oh. Marker size. Oh. Well, cool. That's fine. You can't change a singular one. When does this model extrapolate? This is where I usually see a mistake. It's a small mistake, but it can sometimes catch people because they forget this. The model extrapolates outside the bounds of the x's. So anything within, like these data points right here. Now, this is not an extrapolation, but this is where extrapolation begins on the high side. So people are usually pretty good at saying extrapolation begins up here because your model, if it were to make predictions, doesn't have data to make predictions on. So everything here over after that point is an extrapolation. You're not extrapolating on this point. Anything from that point over would be extrapolating from the model. But the mistake I often see people make is that you are extrapolating down here too. So the model below the lowest point on the x's would also be extrapolating down here, and this model doesn't have data. Just look, there's no data. How do you know your model works on that if there's no data to nail it down? So the idea of extrapolation is anything above a weight of 305 would be the model extrapolating to predict someone's height, or anything below a weight of 86 would be extrapolating right here. And yeah, it might be real data right there. If you are 4'10", you might weigh 86 pounds. Possible. And that's got it. That's extrapolation. Let's head back to the main screen and do some more probability. Okay, probability time. Get some probability going. So I think Tiffany's question, chapter 12, probability, a dresser drawer right here. What is the probability of selecting shirts right here? Let's go look at some chapter 12 probability and then some 474. So chapter 12 with probability. Chapter 12 is all about probability. We'll be doing that next week. It's a pretty good chapter. It's very mathy. We just did a chapter that is not mathy. Now we're jumping right back into the math. We're getting closer to the next exam. Next exam is coming up right here, right? Let's go see. Next exam for Stat 201. I swear, exam 2 just... it's like immediately here. Exam 2, it's coming up here on Wednesday, October 27th. It was 3 weeks from yesterday. That's not too far away. It's not too far away. And yeah, we'll be doing all the sampling stuff. And then we'll put confidence intervals. Nice. So we don't have that much more. We're good. Not too much going on. We got so much time. So we have 2.5 weeks. We'll review on Wednesday. Good stuff. I'm making my plans in my head right now. The coming chapters are not easy ones, though. They're not hard. What are they? They're ones that you need to practice. I sent you an email about the cursor thing. Oh, of course, Tara, anytime. With the coming chapters, there are things that people are not going to know before this class. So make sure you attend class. I say that all the time. But you'll just have to practice them. They'll just be like, okay, let me practice the assignments. Let me look over the videos, and then I can get it down. The material will be slower because we only have 3 more chapters to cover in 3 weeks till the test. So it's going to be a little bit slower. 2 + 2 equals... oh, ditto. Why are you asking those tough questions right there? 100 points. Put the answer in the chat. I don't know the answer. Let's check this out. So we have 8 blue shirts. Here's one of my blue shirts. We have 10 red shirts and 7 black shirts. So probably it would be best to draw this out. Let's go think what we have right here. So in this dresser, why am I... oh, that's all right, Jake. Jake, 100 points. Thank you for swinging by, Jake. We're doing probability right now. And we are talking about the shirts. We have black shirts. Oh, I should have just saved that. Okay. So we have here 8 blue shirts. We have here 10 red shirts. Ooh, crazy red shirts. And we have here 7 black shirts. So what is the probability that a randomly selected shirt will be red? How many shirts do we own? A lot of shirts. More shirts than I own. I probably own like 12 t-shirts. Double my t-shirts. I have more, but they're in storage. My ears going crazy. Sorry, everybody. How many t-shirts do we own? We're just going to go into the door and just grab a shirt. Sell me t-shirts. We own 25 t-shirts. So if we just reach into the drawer and grab a t-shirt, the mathematics for this is x over n. So x being the number of possibilities that satisfy the trials, which is 7 over the total, and n being right here, n is going to be 25. So the mathematics for this is there are 25 total t-shirts. Is it black we're looking for? Red? Oh, red. So we don't want a black t-shirt. We want a red t-shirt. We can actually solve this one. That should be 40%. Yep. So 40% right here, just make sure to solve. That is the percent right there. What is the probability that a shirt is not black? Well, a shirt will either be black or not black, and we're actually going back now and talking about the complement rule. The complement rule is 1 minus something. So the complement of an event is 1 minus it. So what's the probability of a shirt being black? So the probability of a shirt being black is what? Like, what is probability of a shirt being black? Probability, just the probability of a shirt being black. Reach in the drawer, and what's the probability of grabbing a black shirt? Probability of a black shirt will be what? Just reach in the drawer and grab a shirt. Was it a black shirt? Probability of a black shirt, I know it says not black. So the probability of a black shirt is this. Why you do that to me, crayon pen? Hate that pen. Probability of a black shirt is this. But now we need to figure out the probability it's not black. So tell me, the shirt is either black or not black, right? So the shirt will either be black or not black. And one of those things must occur. So now, and that's it right there, if we know the probability of black is 7 over 25, then we can solve here for x. It's a bit of showing all the mathematics for it, and that will equal up to 1. So the mathematics for it is simply going to be to take and just say, well, it's either black or not black, and we can subtract off from this 1 minus 7/25. And that is going to give us 18 over 25, which my brain's clicking away right now. Brain, do it. So let's see right here. We'll times it by 4, Brian. Times it by 4. So that'd be 3264, right? 0.64. Oh my gosh, Brian's brain didn't work. So it's 18 over 25. Oh, it's, wait, 18, 36, 62? Brian, your brain's not working today. Wow. Easy. 72. Oh my God, 36 times 2 is 72. Don't do things in your head. Do it with the power of a calculator. So 7 divided by 25. That's when Brian needs some sleep right here. So 1 minus this right here. 7 divided by 25. 1 minus this. 7 divided by 25. Copy, 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 copy. 1 minus. There we go. It also can be done as 18 over 25 because we could just look at right here as Brian's brain just doesn't work. I was just seeing if everyone was paying attention. So it could be done as 18 over 25 because you can see right here, either a shirt is black or is not black. A bunch of ways to look at this one visually right here when you think through it. Either a shirt is black or not black. My brain's just not full throttle today. Need to get that second cup of coffee. The basic arithmetic is the hardest part. But does this make sense here conceptually, Tiffany, that either a shirt is black or not black? Those are complements of each other. If a shirt is not black, it'll be either blue or red, and the probability of blue or red. So another way to solve this could be, like, we can do an alternative solve of this problem. Because if a shirt is not black, it'll be blue or red. So the probability of red... Microsoft Word, you're not my friend. There's a probability of red plus the probability of blue equals to the probability of red or blue, which is the probability of not black. Nice job. Great job there, Tiffany. Yep. A lot of great questions. Chapter 12 is a good one to practice the mathematics on and to know rules right here, which is the addition rule. So a shirt has to be either red, like this is a blue shirt. I know it has red on it, but I would say this is a blue shirt with stuff on it. I mean, like if you took off this, it would just be a blue shirt. So This is the probability of a red or blue shirt. Probability of a red shirt is 10 over 25. Probability of a blue shirt is 8 over 25. A shirt is either red or blue. There is no overlap, i.e. they are disjoint events. You'll hear a lot of this terminology as we go through this. So even though this problem is pretty simple, it's got some complex topics in it, and you can always make that math error. So double check. I didn't get the 100 today. Tiffany did. Another 100 points there for you, Tiffany. We're going to do some 474 now. Check it out. Let's do this. I'm just seeing if people are catching my mistakes. That's all I do. I make mistakes so you can catch them and you can learn. Nah. Every once in a while, the coffee doesn't kick in. Okay, let's check out some 474. I think it was some question 2 for 474, right? Question 2, I think. Question 2, I think. 474, if you're here, it is your time. Our time down here. I'm trying to find where it was at. I think question 2. I think. Oh, it's 320. It's 320. Thank you, Lillian. 50 points right there. Correct to me. 320. Let's go look at some 320 question number 2. That's why. My brain was like, what? Lillian, thank you so much for being here. Another 100 points, Lillian. I just throw out crazy amounts of points, especially during office hours. So we've got here the next assignment for simple linear regression coming up here due on Friday. So, that's activity. Let's take a look at the activity. We'll be doing it probably tomorrow, maybe. So here we are at the simple linear regression. Okay, let's download the RMD. Question number 2. Let's take a look at some question number 2. Juliet, good to see you here. Hey, Colin, I'll have to check out the email. I'm excited to see what it is. Let's check out question number 2 for assignment number 6, BAS 320. Yeah, it's pretty response heavy for 474. And so we're just going to hop down here. Look at this. Boop. Awesome. Load in the housing data using the data command. Oh, we did it for you. Now you might say, Brian, this doesn't load. Who here knows if this doesn't load, what is going on? Someone's running this right now and saying it's not loading. What would you tell them to do? Where is the EX3 housing data? Now I've already had this loaded in, or I have this turned on. So where's the EX3 housing data? And why is this not loading in for someone? Where's the EX3 housing data and why is this not loading in? Good thing to know. It's like, oh, this is, and you can also have the answer to it. Important to know these little things, and you can see the answer right there. So for 50 points, where is it? Where does it live? Yours might not be saying this because this wouldn't be on right now. It's inside of, yep, Lillian right there. Great job. Make sure you have library reg class loaded in. And so you've probably already done this. It's earlier in the assignment. Usually we do these things at the start, and there's library reg class. So if you've jumped down to this question and you're doing it, I just like to mention these things because it doesn't hurt to load it twice. It's not needed, but so now it should work for everybody. So we're using the oh man, oh, we're gonna make a model right here. Okay. I am so Brian sometimes does. Let's do this. Brian does similar but different work. I cannot put this enough. I'm going to do similar but different work. So it literally tells us what to do right here. Mostly with writing out these things right here, defining the transforms. Oh, we're doing transformations. So with right here, so we're going to define the Y trans and the X trans. We're going to have to make a model right here. And I think we are transforming them. So let's talk a little bit about transforming variables right here and how to do that. So we need to look at the EX3 housing data. It's only got 2 variables, so I know which ones we're using. Yeah, let's do it. Why not? Why not? Let's do it. Okay. So when we make a model, we're going to make a linear model right here. And to make a linear model, we're going to go here and predict the price of a house, capitalized, from the area of a house, y tilde x comma data equals data frame. And so this is the linear model. Now, we're probably going to see something a little bit crazy with this, I'm assuming, because we're going to do some transformations here. To visualize this model, the easiest way is to visualize it with visualize model M, and I'm seeing some issues. You'll notice right here that there is heteroskedasticity. Major heteroskedasticity. The plot is thickening in crazy, absurd ways. Let me look when this assignment is due again. I think it's not due for a little bit right here. This assignment is due on October 10th. on Sunday. Okay, so we have a class today. I think we'll get through this today. We should be good. Woo! Yeah, we don't have that much to cover today. We got conditions and transformations. Yeah, we'll do it. We're fine. This model has issues. What do you notice over here maybe a little bit? Do you see the major issues of the model? Is it straight enough? Yeah, probably. I mean, a line mostly goes through the data. So QQ, it is two quantitative variables. Is it straight enough? Probably. Is QQ straight enough? No outliers, little bit of outlier issues. Maybe is that a point up there? Or is that oh, that's a point. Thought it might be a speck on my screen. And then does the plot thicken? Looks like we have plot thickening. Now, one thing we should look at, and remember I'm doing similar but different work. I can't highlight this enough, is we should look at a check regression, which will be a major portion of today. Check regression right here is going to check the regression. And now we are looking at Stat 201 should know what is the name of this thing right here. Stat 201 has covered this a lot. This is important topics for 201 and 320. The graphic over here on the far left is on the 201 second test. So what is this called? So if you're 201, you're listening in, you should be like, oh, I know what this thing is called. It's kind of right there. So what is this thing called right here that shows us all the residuals at one time, which is how much we miss by? It takes the model, which is the linear model, and makes a plot from it where it takes the line and makes the line flat, showing us all the residuals. I think that's that point that I couldn't see just barely off the top of the screen right there. So if you look at this, it's going to make what's it called? Important to know what this is. This is called a residual plot. A residual plot shows us all the residuals at one time. Every single residual is graphed right here for us to see. And we can see all of them at one time, seeing that we do have an issue of heteroscedasticity, or as Stat 201 would say, the plot is getting thicker in some spots. Now, it could get thicker or thinner, but we don't want to see this. We want to see equal spread throughout, and we don't like that. Next, we would look right here and see that there's other issues, such as the normality of the residuals, major problem. But I'm going to walk through this step by step and analyze how we should read this output. So please follow these steps. This is majorly important for the test. So for the test, here's what you need to know how to do. When doing check regression, step 1. First, look at p-values. If any are below 0.05, you fail. Now, this is counterintuitive because usually people think a low p-value is good, but the null hypothesis is that the linearity is good and we fail linearity. The null hypothesis is that equal spread is good and we fail that equal spread is good. The null hypothesis is that normality is good, as in it's normal, and we fail that assumption. So we actually fail all of these, so this is a problem with this regression. So step 2, if you failed some assumptions, make sure sample size is 25 or greater. So do we have, yes or no in the chat, do we have at least 25 sample size? Do we have at least 25 sample size to continue on? Do we have at least 25 sample size to continue on? Like, do I have a sample size of at least 25? It even says down here, advice, if the sample size is less than 25, all these tests must be passed, and we fail every one of them because they're below 0.05. So we do, Lillian, great work right there. Yep, we have a sample size of 522, so we can continue on, and this actually tells you step 3. If the sample size is greater than 25 and tests are failed, look at the diagnostic plots. So that's literally step 3 right there. So that's listed for you in the output. Step 3, if you have at least 25 sample size, look at diagnostic plots. So this is where we're going to look at the diagnostic plots. Good to see you here, Lakeisha. Brian's here is acting up today. And when we look at the diagnostic plots, we can look at all 3 conditions. Condition 1 being linearity is this line right here. Let me draw on this. So the linearity condition would be evaluated right here. Does the line go through the data? Does the line look to mostly go through the center of this data right here? If you look at the data, which goes around it, does the line look to mostly go through the center of it? And so don't look too crazy at it, Bo, but does that line look to mostly go through the center, yes or no? Like if I were to draw you a picture, and then I had a line like, let's say some dots are here. And then I asked you, does the line right here go through the center of those dots? The answer would be no. This would be no up here. Does that line look to mostly go through the center of that data? Like if it's spraying out like, does it go through the center of it? I'll draw you a really good one up here for an example. So if I had data that looked like this, does the line go through the center of that data? It actually doesn't look too bad right here. So the line looks to kind of go through the middle of that data. There's other issues. So that we're about to see some other issues. So let me ask a big one. And so you might see it here. I'll delete some stuff. Does the spread look constant? So now we're looking at this. Does the spread look constant right here? Does the amount that it goes out, like from the line, does it look constant? Is there equal spread right here? This one's a very obvious one. This one no statistician would debate over. No statistician's going to debate over this one right here. Does that spread look constant? So does the spread around the line, like around the line, does it look constant? Which is the equal spread condition. The homoscedasticity versus heteroscedasticity. So that's where we look at equal spread right there. So we're examining the equal spread, which we failed. So for equal spread, I would say what? So is that a constant spread around the line or a differing spread around the line? It does not look constant. I knocked over my mug, and I literally half caught it. That was lucky. Almost broke my Mario mug. So now the last condition is the what condition? What is the last Great job right there, Lillian. What is the last condition? The last condition is the what condition. The last condition is the what condition. So what is our last condition to look at right here? Our last condition will be what? So look over there on the far side screen, just kind of memorize them. Linearity, does the line go through the data? Does it have equal spread? And the last condition is the what? The normality of the residuals. Great job right there, Lillian, another 50 points. The normality of the residuals is the last condition. Now, to look at the normality of the residuals, we need to always look at the QQ plot. Notice how the QQ plot says values of residuals if normal. So if it's good, it will follow this line. That's the good one. Does this look good or very bad? Does this look good or very bad for the normality of the residuals? The normality of the residuals should be analyzed by the QQ plot. And does this look good or very bad? Does it look good or very bad? That's how I would mark it. This looks very, 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 very what? Looks pretty bad. Looks very bad. So this is very bad. It does not follow the normality line, which is what we would expect given normal. So we are observing values that do not follow the normal curve. Don't look at this right here. Don't look at the histogram. It's just there to trick you. Not literally, but don't look at it. We're going to look at the QQ plot for normality and say that we have evidence it's not normal. So this is where we would do transformations, which is the point of this question. So we do have problems. This regression, I would say like analysis. This regression is not a good reflection of reality. We definitely fail the normality of residuals and equal spread. We should try transformations to see if we can improve the model. So now, can't remember if we're doing it this one, but I'm going to do find transformations. And here's what find transformations does. It gets mad because my screen is not big enough to store the plot. Find transformations is going to look through here and find transformations. Now, the log-log model might be mentioned later on. The log-log model is a possible model that we could choose. We're not going to choose it, but the log-log model is a possibility. Here's what my data looked like with no transformation. It has a bigger spread going out. So this is my data with no transformation, and it should report the R squared, but this is the highest R squared. whoa, wait a minute, look at this. What do you notice is better about this model here? What do you notice is definitely better going from this, my original model, which we just were looking at a moment ago, and you notice this right here versus my model over here? What have I kind of improved by transforming the X and the Y, by raising them? I raised the price to the negative 0.075 and the area to the negative 0.75. So they're both being raised to that value. I'm raising them to a power and transforming them, doing like a reciprocal root, a root reciprocal, or third power, fourth root reciprocal. Weird transformation. But what do you notice about this? What do you notice about what I'm trying to point to about here by doing this across it? I'm kind of going up and down the same amount. Where over here, I'm not going up and down the same amount. I'm pointing to you that there's the what is much better for this model. QQ, straight enough. No outliers. That one's looking better on the last condition. Stat 1 should know. 2 quantitative variables. Straight enough. No outliers. Kind of improve that a little bit here. But also, we see that this is massively improved. The spread looks more even. It's an even spread across. So this has less of a plot thickening issue for Stat 1 if you're listening in. And great job, HGT, hanging out. 474, practicing up your knowledge. Love it. So you can see your best transformation right here. No transformation gets an R squared of this. We're increasing the R squared, which is the percent of variation Y explained by the variation in X. And if we want to transform these variables, we need to take the power of the Y. Remember, Brian's doing similar but different work. I can't point this out enough. We need to take the power of the Y right here, and we need to store into Y trans. And the Y variable is price, but price is in the EX3 and price. And then we are going to raise it to this power. And we are doing the same thing with the X, and I'm just storing these as vectors in the global environment. And so the reason I'm raising X to the same power, you probably won't, I think, for this question, once again, similar but different work, is because I'm choosing the top power right here, which says raise your X variable to this power, raise your Y variable to this power, and now I am storing this right here. So I've defined my variables right there. There's the defining of them, and now I need to fit the model. The fitting of the model is the same way, but I'm going to call it mtrans for my transformed model. You can just call it whatever you want, but this makes most sense to me. We're going to use y tilde x, but there's not going to be a data equals because these are just vectors in the global environment. What do I mean by that? Well, sometimes we have vectors in a data frame, like the EX3 data frame has the vectors inside of it, hence the $ connecting the data frame to the vector. But these vectors right here were stored to the global environment, so they just exist out there in the ether. So we are not doing data equals right here because they're in the global environment, not inside of a data frame. Here's our model fit, graphic error, love it. No graphic error. And so we fit the model. The visualization of the model will be the same visualization we just saw, but a much bigger version of it. Make sure to do your transformed model. And too large, that's all right, we fixed that. Looking pretty good, looking much better. Looking much better, now we need to check it again. So let's check the model right here, check regression, and let's take a look at the transformed model and see what we got. Oh, wow. So let's do the 3 steps again. This is really good practice. These questions are on the test. So you ready, Lillian? I want you to practice these 3 steps right here and see what you get. So do we pass linearity, yes or no? So this is where people are going to make mistakes. Do we pass linearity, yes or no? So read the step 1 right there. Look at the p-values. If any are below 0.05, you fail. So do we pass linearity, yes or no? As in, does the line. So we're going to look at the p-value, but does that line go through the center of the data? Do we pass that or fail that? So pass would be yes. Yes, you're perfect. And that's where people make mistakes is they're like, oh, high p-value bad. No. If the p-value is high, you pass it. So that's where people make the mistake right here is, and if you look at it, it actually looks good. How about right here? So I'll answer the last one. How about on the equal spread now? And you look at that equal spread right there. I mean, look at it. It goes, I mean, it's not perfect. Nothing's going to be perfect in statistics. But if you were to look at the spread of this and look at the p-value, I've got the p-value highlighted. The spread goes like this. Maybe I shouldn't do it in red because I don't want to imply that. Spread goes something like this. Spread goes, I know it's not perfect. It's not perfect. Nothing's perfect in statistics. Do we pass this? Yes or no? Nothing's perfect in statistics. Nothing's going to be perfect. Yes, it passes as well. And you don't even look at the plot now. Don't even look at it.
It doesn't matter.
Because we're only looking at the p-values right now. Step 1 is to look at the p-values. We're good. It's actually the best one because it has the highest p-value. Last but not least, the normality. And look at this. Remember our previous one a while ago? I might have deleted it. I did delete it. But the previous one we had a while ago, which I can show much quicker. The previous one we had a moment ago looked horrible. Now compare that to where we're at now, and the p-value is much higher. We're all right. It passes. But look, it's following the red line. The p-value is higher. But when it didn't follow the red line, the p-value was lower. This is one that fails. Like everything right here is indicating failing. The only one I really don't see it with is with the linearity, even though we fail the linearity of the model in the x variable. But over here, we have great conditions. The line definitely goes through the center as far as we can tell. We don't have any evidence against it. And then the equal spread looks to be there, looks to be good. And then the normality of the residuals is amazing. I mean, okay, it's not amazing, but we're lucky. That's a very hard one to pass usually. So our model has drastically improved the regression, and also the R squared of our model went up. The original R squared of our model being 67.2% of the variation to now 63.76. And this would be an increase in the what significance of the model. I'm just going to take these numbers right here and subtract them, because when I talk about R squared, very important thing, this is a 6.4% increase in value of R squared. This has increased the what significance of the model. So this has increased the what significance of the model. By going from an R squared of 67.2%, to an R squared of 73.6%, I have increased the what significance of the model. What have we increased the significance of the model in? It's increased to what significance of the model? Practical, Lillian, you got it. Practical significance. I think we're going to end here because 30 minutes till class. I'm going to get ready for class. But so, Lillian, if this is making sense, you've got a huge head start on class today, and you'll be good to go because this is the majority of today's lecture. Checking regressions, doing transformations. If you understand this, you're good to go. It's going to be a fun class, a lot of work. With that, we're going to head off here, everybody. We'll do this dramatic ending. We'll be back teaching here in 30 minutes. Bye for now, everyone. Bye. You're welcome, Lillian. Excellent work.